Okay, good morning. Today I'm going to discuss about the introductions to rotational spectroscopy with different types of, with discussing a few questions. So first, I would like to introduce what is the uh, microwave spectroscopy is all about. Whenever there is a molecule, it can be either linear or it may not be a linear molecule, and depending on their way of way, it can be in a one directions, that is in a three-dimensional. If we imagine, then it can be either in the x directions, or it can be either in the y, or it can be in the z. Here we will discuss the moment of inertia about the molecule, about the three perpendicular axis. So if you see here, so I'm showing here, it's the three-dimensional body. So it's the 3D body. It's the 3D body, which is which is very complex, and it's all about the three perpendicular axis. So if you consider this one is the y, and this one is the x, and this one it will be the z direction. And due to x, y, z directions, we can explain a molecule in the x, y, z directions. And based on that, we will apply it the principal moment of inertia, which can be considered as the IA and IB and IC. Okay. If I say IA will be at the moment of inertia along x-axis, and then IB will be the moment of inertia in the y-axis, and IZ will be the moment of inertia along the z-axis. So all the molecules can be resolved into three axes, that is x, y, z, and based on that we can classify it into the groups according to the relative values of three principal moment of inertia. So here it is IB, IZ, and IZ. So all the molecules may have dipole moment. So based on dipole moment, they will be considered as the plus and minus, as shown here. So if some part of the molecules is the positive, then the next one, the bottom will be the negative. Similarly, if it is rotate, then plus one will be comes to here, and minus will be goes here. So that's why this one. And here the molecule dipole moment, if it is downward, here it is towards the left hand side. And similarly on another rotations, clockwise rotations, so the minus one will be here, and dipole moment will be towards this one. So if we communicate it in a vertical component, it's a look like a wave, which is like that with a variation of time. So here is another example where here is the molecules, where is the asymmetric stretching, and all will have to be discussed in the later part on the IR spectra. So the basic point of the rotational spectroscopy is that the rotation of three-dimensional body may be resolved into rotational component about three mutually perpendicular axes through central gravity. As already I have shown that there will be IA, IB, and IC based on three principal axes along the molecules. So let's see if ACL or the linear molecule, the molecules will be rotated along the axis, or it can be in the one direction axis. So based on that, first the bone axis is this one, say the x-axis. So if you imagine its rotations, it would be in over in the plane of the paper. Okay, just go to the earlier. You just see that molecules will be rotated in the plane of the paper. So if it is look like that, if it is a bone, if it is bone, so it will be rotated accordingly in the bone, up, down, slowly again, and it will be like that on the plane of the paper. and it is called the end over in rotation at the right angles of the plane. And since it is rotating in the x-axis only, so its value IA along the x-axis will be considered as a 0. And since there is no one to represent along the y and the z axis, so both IA and IB will be the equal. So similarly, for the other molecules also will be considered like that, those which will not be linear and etc. So I will comes to these topics, that is the symmetric tops, what is the prolate oblate, and other part on a different class. So we have already given it in another class where I will discuss what is the symmetric tops, what is the asymmetric top, how to denote it. So basically for right now, I'm just avoiding this part. So already just it's a rewind, IA, IB, and IC when it will be equal. So all will be discussed in the presentations on the earlier one, which I have already been given. So here, let's discuss it, the rigid rotator model. What is the rigid rotator model? So let's discuss it by considering equations in which it is given that you are being asked to show that for a diatomic molecules means two atoms, either it's look like AB or the A2 or it can be B2. But basically we will discuss it for AB, not for the similar molecule or the homonuclear molecules. So it will be discussed for the heteromolecular compound. So let's take the example for the diatomic molecule. So here the moment of inertia is given by I equal to mu r square. You have to prove now that moment of inertia is mu I square. What is the I me represents? It's the moment of inertia. What is the representation of mu? It's the reduced mass. Okay, and r is the radius of the molecules. So let's discuss it. So let us consider two molecules. One is 1, another one is 2. If the mass of one molecule is m1, if the mass of the one molecule is m1, then for the another it is the m2 is the molecular mass. If I considering the mass of atom 1 is m1 and another one is m2, and having m1 is greater, then its center of gravity will be lies more towards the 1, since mass of m1 is higher. So that's why center of gravity will be, let's imagine it will be here. Okay, it will be here. So center of gravity more towards m1, rather it will be more towards m2. So if I consider the distance from the center of the m1 and center of the m2 is r0, then r0 will be equal to be r1, which is the distance from center of the atom m1 to the center of the gravity. And similarly, m2 will be discussed, r2 will be considered as the distance from the center of the m2 to center of the gravity. So hence, I can write out R0 is equal to R1 plus R2. If the molecules rotate about the center of gravity as shown below, so it will be balanced about the center of gravity, and hence the M1 R1 should be equal to M2 R2. So this one for the first one, and this one for the second one. So both have to be equal, since they have to be balanced out. So since it is the balance, and since it is the as we all know that the moment of inertia is the m1 r1 square or mr square, so that's why total moment of inertia should be I is equal to m r1 square m2 r2 square. So you all know that m1 r1 equal to m2 r2. So, and moment of inertia is represented by mass of the component into radius of the component square, or the radius of the square, radius square. So hence, I just write it, total moment of inertia will be m1 r1 square plus m2 r2 square. As you know that m1 r1 is equal to m2 r2, therefore I can write these equations as m1 r1 into r1, right? Since m1 r1 is equal to m2 r2, so is equal to m1 r1 is equal to this one. Okay, r1 already, this one is r1. Since r1 into r1 is equal to r1 square, so I can replace it out by m1 r1 in place of r2 m2 r2 r1. Similarly, for m2 r2 square, I can replace it out by m1 r1 r2 square r2. So now basically r1 and r2 will be the common out. So let's common it r1 r2, since they are the common in the both term. So when I take r1 r2 common, the left out will be m1 plus m2. And since again, if it is m1 and r1 is equal to m2 r2, and if I replace out r2 in r minus r1, since r0 is equal to r1 plus r2. So that's why I can write down r2 will be equal to r0 minus r1. So that's the way to replace it out. Hence r0 minus r1 is written in place of r2. So therefore r1 can be written r1, so m1 can be shift to here. So if you imagine now that m1 r1 is equal to m2 r0 minus m2 r1. So I just, if I shift the m2 r2 to the left hand side, it will be like this one, m1 r1 plus m2 r1 is equal to m2 r0 will be the remaining, and hence if I common it out r1, so if I common it out r1, it will be m2 r0 divided by, here m1 plus m2 will be left out, m1 plus m2. Hence r1 is written as m2 r0 divided by m1 plus m2, and r2 is similarly for r2 m1 r0 divided by m1 m2. And hence if I substitute out both the values of r1 and r2 in the above equations, that is r1, so it will be left out as m1 m2 divided by m1 m2, where the particular value m1 m2 into divided by m1 m2 is called as the reduced mass, which is denoted by mu and is called reduced mass of the system. So here is the expressions to the rigid rotator diatomic molecule, and it is the moment of inertia about the point C. Let's come to the another discussions where you are being asked to discuss the rotational spectra for the diatomic molecules. So here you need not go to the details of the Schrodinger equations and its solving out. Just you have to remember that the Schrodinger's equations give equations to find out the different rotational energy level allowed to a rigid diatomic molecules. And for the rigid diatomic molecules, rigid means they will be the fixed. So for any rigid diatomic molecules, that its value will be expressed as Ez is equal to h square divided by 8 pi square I j into j plus 1, where j represent the rotational quantum number. So that means their energy level is about stepwise. If it is 0, then it will be ground state. If it is 1, then first excited state, and accordingly. So basically, this will be represented by a few lines will be there. So let's see here. Okay. So if I draw out one line simply here, if it is j is equal to 1, 0, then the next one will be considered as j equal to 1. And accordingly, it will be continue up to infinity, infinite numbers of lines. So this is the way. So you have to remember the equations for further discussions of um, microwave spectra. So in the rotational regio spectra are usually discussed in terms of actually wave number. So whatever we have already written out there is a Ez, which is representing the energy. Now Ez will be converted into Ez. So here it is representing energy. Here it is representing wave number. Wave number is simply Ez divided by AC. So if I place out the value of Ez divided by AC, it will be 8 pi square IC J into J, where J equal to 0, 1, 2, 3 as accordingly. And as usual, I representing moment of inertia, C representing velocity of light. So if these particular terms, so if the whole this particular term, if we replace it out by B, then it will be B, J plus 1. Okay, so I just replaced out B. And B will be commonly called as the rotational constant. Okay, so value of B will be 8 pi square IC. Here C is the velocity of light. It can be IB, IC, or IA also. Okay. So let's come to the what is it now? Here it is the way how to calculate the rotational energy in terms of rigid diatomic molecules and what would be allowed and what will not be allowed. So since Ez is equal to B J into J plus 1, so if I place the value of J 0, then it will be simply B, simply 0. So that's why it will be 0. If it is value of J is 1, then it will be 2B. Similarly for 2, it will be 6B, and accordingly it will be increasing. So it can be increases up to infinity also. It can up to infinity also. So hence it can, for our to limitize it out, so we are considering up to J equal to 6. So here is the diagrammatically representation of rotational energy of rigid diatomic molecule. If you observe, if value of J is 0, if the value of J is 0, then its value comes out to be 0, or wave number comes out to be 0. If it is J equal to 1, then it will be twice B. Means this is the minimum rotational energy or the lowest angular momentum that can be possible. And if we continue to calculate out Ez, so with increasing J values, it will have no limit to the rotational energy, and molecules may have to be increasingly accordingly. So here it is 0, then twice B. And if you look out the difference, here it is the 2B will be the difference. Between 6B and 2B, again, it will be difference of 4B, just increasing 2 times. Okay, then this one is increasing 6B. So 2 plus 2, 4B, 4 plus 2, 6, and 6 plus 2, 8. So here it will be difference of 8B. And here it will be difference of 10B. Here it will be difference of 12B. Just increasing nearly 2 times. Okay, so 2 times it will be increased, or sorry, it should not be 2 times. It should not be called 2 times. It should be increasing 2B value with each difference of energy level. So in practice, of course, there comes a point at which the centrifugal force of a rapidly rotating diatomic molecule will be greater than the strength of the bone, and the molecule is disrupted, but disrupted at the point, but the point is not reached at the normal temperature. Okay, so here will be the part of the discussions. Now let's come to the another important topic that is the frequency of spectral lines. So let's come to the what is the meaning of frequency of spectral line. When we consider the value j equal to 0, it represents the ground rotational state. That is, the molecule will not have any rotation at all. Okay, we can let incident radiations to strike it so that it will absorb the radiations and it will rise to the state j equal to 1. That means energy lies initially j equal to 1. Say j equal to 0. When I strike it with a certain amount of incident radiations, the molecule will be jumped to j equal to 1 state. Okay, so the difference between these two, as already been mentioned, is the twice v, and hence it can be written mathematically as sin E j equal to 1, or wave number 1 minus wave number 0, and the differentiate, if we differentiate out, it will be 2b. Similarly, if we differentiate out between 1 and 2, the difference will be same way, E2 minus Ej equal to 1, and its values comes out to be, for 2, it is the 6b as we have already calculated, minus 2b, which comes out to be 4b, which cannot be possible. Hence, the energy difference or absorption line will be appeared only at 2b centimeter inverse. So molecules have to be active, or molecule have to be rotationally active if there will be an energy difference or wave number difference will be twice b centimeter inverse. So hence energy difference between two successive lines will be always constant. And in general, to raise a molecule from j equal to j plus 1 state, the minimum amount that needed will be twice b j plus 1 centimeter inverse. So here it is for the 2, it is the 6b, and for j equal to 1, it is 2, so the difference will be 4b. So hence 2b, if I minus it out, so again it will be 2b centimeter. So hence molecules will be active at this point only. So here it is the case from 0 to 1, from 1 to 0 so these are the part. So all the allowed energy transitions will be 2b, then 4b, then 6b, 8b, 10b, 12b centimeter inverse will be the case. Or these are the absorption band. Similarly, emission band can also be observed when j value will be the negative. That time it will be minus. So whatever I am just saying, or whatever I am just showing you in the PPT, you just screenshot it out. Okay, so whatever the questions or whatever the discussions, so basically based on the here will always leads to the proper valuations in your exam. So better to just screenshot out each and every slide. So whatever I am showing here, and it will be beneficial for you. Okay, so already, so let's finish it out. So for a stepwise raising of rotational energy in an absorption spectrum consisting of lines at 2b, 4b, 6b centimeter inverse, while a similar lowering would result in an identical emission spectrum. So now let's come to the another point, that is the selections rule for rotational spectrum. So we have already seen mathematically that there will be the possibility of rotational spectrum at 2b centimeter inverse, 6b, 4b, 6b, 8b, like that. So by increasing 2b additional of 2b centimeter inverse will be on each different rotational analysis, rotational level. So in order to give rotational spectra, the molecule, the first criteria is that the molecule must have permanent dipole. Okay, any molecules which will not have any dipole moment can show rotational spectra. So first point is that the molecule must have the permanent dipole. So remember one thing, the molecule must have permanent dipole. This is the first and basic criteria for the selection rule. There will be the many questions in earlier paper that what is the selection rule for rotational spectrum are being asked. So whatever the questions it will be on related to space selection rule for rotational spectra, always write down it. Many people just forget to write that molecules have the permanent dipole. So molecule must be needed to be permanent dipole, permanent active. That means either two poles must have it to be there, either plus or the minus one. So second point is that the rotating diatomic molecules can be thought of an interactions with the electric field of the radiations. Okay, so molecular rotations, whatever the molecule will be rotate in a line, whatever the molecule they will rotate, they can be rotate in x-axis, maybe y, maybe z, in any direction. It must have to interact with an electric field. Okay, so it has to be electric. Already I have shown that the molecules can be imagined in a wave pattern, and that wave has to overlap with an electrical field of electrical field, followed and allowing energy to be accessed between the molecules and the rotations. Okay, so here's and ultimately there will be a restrictions on the rotational transitions. Each transitions cannot lead to transitions cannot lead to a permanent a rotational spectra. The molecule must have to be permanent dipole, but each rotation transition cannot lead to rotational spectra. So whatever the rotation, whatever the transition, that must be del J value, del J, or the difference of the value should be either plus 1 or minus 1. It should be the must. So just remember these 2 points, and you have to go through that. First one is that the molecule must have permanent dipole, and second one is that the del J value should be either plus 1 or minus 1. So any transitions cannot lead to the rotations. That means if rotations can occur from 0, 1, 2, say if there is transitions between these two. It is here it is J equal to 0, here it is J equal to 1, here it is J equal to 2. The first transitions can be an active rotational spectrum, but second one will not be an active rotational spectrum since it is jump from J equal to 1 to J equal to 2. That means it is not its del J value is not equal to 1. Okay, so how not why it is not equal to 1? If I minus it out, J final minus J initial is 0, so it is 0. J final is 2, so 2 minus 1 is equal to 2. So del J value is not equal to 2. That's why all the transition cannot lead to rotational spectra. The criteria is that it must be either plus 1 or it can be either minus 1. So just remember or mug up these things, that del J value should be plus minus 1. So for absorptions, always for absorption, del J value should be minus plus 1, and for emission, del J value should be minus 1. Hope you understand the selections rule. So basically, these are the 3 main postulates, important part of the rotational spectra. First one is that rotational, the moment of inertia. Second one is the equations, that is EJ and the in terms of energy or in terms of wave number, in terms of joule and in terms of wave number. You need that particularly and specifically, and through that you have to go through the different numerical calculations also. And thirdly, you need the selections rule for the rotational, and in the that 2 point, which is the most important one, is that one says that molecules must have to be permanent dipole, molecule must have exist permanent dipole, and second one is that it molecules rotations either will be plus 1 or it should be minus 1. So that's the part. So here I'm going to show that completed out. So here are the few points which you may go through. that it is evident that transitions are occurred only when there is a increase or decrease by unity in rotational quantum number. That means del j equal to 0 to j equal to 1 will not be lead to rotational spectra. Similarly, j equal to 2 to j equal to 4 will not lead to rotational spectrum. Hence, it is written as spectroscopically forbidden. Forbidden means it cannot be occurred. Okay, so in rigid rotator, del J is greater than Z is 2. That refers the upper state. If I Z dash it out, then it is the lower. Double dash means it is the higher energy state. So it can be either plus or minus. If it is written as this one, then positive one will be emitted, minus one will be for the observed. Since it is J value is the gray. So this is the way how to calculate out what would be the value, and all the molecules of diatomic spectra having 2b centimeter inverse, 4b centimeter inverse, 6b centimeter inverse will be allowed. So sometimes they may ask that which of the following diatomic spectra or which of the following Z values leads to a rotational spectra. So then the users write down whatever the difference or whatever the energy state. So sometimes they may exist or some may not be existed. Now on that, let's come to the last topics of this lecture, that is the effect of isotopic substitutions. Isotopic substitutions can be lead to a disturbance, or having seen that there is a increase or decrease in the different values of B. So how it can be possible? Let's come to the first point. So here it is. So when a particular atom in a molecule is replaced by its isotopes. Okay, isotopes means having same mass number but different. Same atomic number but different mass number. For example, hydrogen 1, which is called protium, hydrogen 1, 2, which is called deuterium, hydrogen 1, 3, which is called tritium. So these are the three isotopes of hydrogen. Similarly, carbon will have C12, C13, fluorine have C8, 19, then 18, etc. These are some of the isotopes. So if I change it out, there will be an appreciable change of internuclear distance, since the value of C will be changed. Value of C will be changed. So already we have shown that two molecules, one is greater, here it is the C, so C will be changed since this one will be constant. See if it is HF. So if I replaced it out by F with another isotopes of heavier isotope, then value of C will be definitely changed. Similarly, if I change the fluorine with another one, that is the chlorine, which is either 35 or 36, so definitely C value will be changed. So that's why the molecules having isotopic substitution leads to change in the internuclear distance. Okay, then here whatever the value of R naught is earlier will not be remain same. So, however, the change in total mass, although the mass and hence the moment of inertia of the molecule leads to difference. So, let's discuss out one example of carbon monoxide. Is an example ongoing from carbon 12 to carbon 13. Here it is the carbon 12 is here, and here I am changing it to carbon 13. Let's maintain the oxygen 1 to remain same. So oxygen is 16, here also oxygen is 16. So there is a mass increase, okay? A mass is increased. From 12 it is the 13. If the mass is increases, so value of B will be decreases. As we have already seen that B equal to 8C divided by that one. So the B value will be decreased. Already we have shown then mass is the inversely proportional to B, or B is inversely proportional to molar mass. So change of B leads to change in internal and change in rotational energy too. So change of value of B can also lead to change in the value of B also. So since the value of B change, the effect will be observed in the different rotational energy level here. If I considered it for, for the first part, for let's say for the CO, this one is for C12O, and this one is for C13O. Okay. Okay, so here I am showing if it is C12, which is having the spectrum, and then here that it will be changed. So its change will be more prominent in the higher spectra, higher part. See, here is the larger difference is observed. Here it is the very minimum difference is observed. Here it is dotted line shows that this particular part of the left hand side one representing C12, and on the right hand side it will be C13. Since it is having higher value, higher mass, so its B is slightly decreases. So here the lighter one is twice B and the heavier one will be the 2B dash. So here it is. And if I represent it out, then this will be the way. Here it is the 2B, then this, there is, if you see that the difference of between the lines is more prominent in the higher state. Okay, thus the effect of isotopic substitution on energy levels and rotational spectrum of diatomic molecules as variations with isotopic substitution or with atomic masses. So for same atom, same molecule, there may be different sort of rotational spectra will be observed with change of isotopes. So here is the part for the to the effect of isotopic substitution. Many common questions are being there for discussing the many molecules. So if they may ask either HF or CO or maybe sometime HCl, maybe they may ask whatever drawing that will be remain same, whatever the difference that will be also remain same. Just try to find out that, just try to figure out that which one is the heavier, which one is the lighter. Lighter one will be the first and heavier one will be the second. So here is the summary up. Now let's come to another important questions which have been asked many times, that you are always been asked to find out which are the molecules that are being active in vibrational rotational spectrum or the microwave spectrum. So if such types of questions been asked, so always try to find out, always try to figure out which are the molecules, which molecules of them will be highly active in active dipole. For example, in HCl, H is positive, Cl is the negative. So definitely dipole is there. So this one is active rotational. CH3Cl, carbon, here is the Cl, here is the hydrogen, 3 hydrogen. Okay. So this one will be towards this one will be towards the carbon, this one bone will be towards carbon. Ultimately, this one is the upward. So dipole moment, this one is also having dipole moment. Similarly, CH2Cl, water molecules also having dipole moment. And in these three particular case, that is the hydrogen, CH4 and SF6, they will not have any dipole and hence they will be inactive in the rotational spectrum. So a few questions such as that you have been asked to find out what will be the value for the calculate rotational constant B, and you are being asked to find out the B. Is the question. So let's read out the questions first. So the rotational spectrum BR, these are the compound, that is BR 79. BR is given 79 and F is given in the 19. Okay, so the series of equidistant lines. So the series of equidistant lines. That means if the lines will be appeared, these are the equidistance. These are the equidistance. Equidistance means twice B. So that means twice B centimeter inverse is been given as 0.71433 centimeter inverse. So this values is given. So if it is given, then I can find out the value of B by dividing the value 7.1433 by 2. So here it is, point is there. So this one will be find out the value of B. So now the second clue is that hence the moment of inertia and the bone length of the molecule. If I figure out the value of B, then I will find out the value of I. So if this is a very simple one. So there, I don't think that you have any problem in finding out the value of I. Now, on the second part of the part, they are asked. Okay, I just minimized it. On the second part, the I can be calculated out since the I is simply for I. already they b for from b is equal to h divided by 8 pi square I into c. So value of I can be calculated out since b known, h known, c value known, pi value already known. So I can calculate out the value of I also. Okay, so these are the I think very simple questions, and you can find out the way to determine. And also they have been asked to determine the bone length. So bone length is bone length from the reduced mass. Reduced mass already you have been known how to calculate of the reduced mass. Here it is both the value for the value of given m1 m2 divided by m1 plus m2 is already known. So M1 is 72 and M2 it will be 19, and hence value of mu will be known. If the value of mu will be known, then then it will be easy to determine the value of R also. So here they are asking us to calculate out the value of R. Either that means what will be the value of R naught, since M1 is known, R1 is known, R1 can be calculated out, M2 into R naught divided by M1 into M2. So same way you can find out now the value. So what are the equations? I is equal to mu R naught square. So here I already find out from these equations we can determine the value of I, and mu from these equations we can follow out the mu, and R naught value can be calculated out. So that's the way to solve out the problem. So try out, and if you have any difficulty in solving the above problem, just comment me. I will provide a link to solution link. Here are another questions in which you are being asked to calculate out the values of B for H17Cl and D2Cl15. Okay, so from here, that is the H35Cl. This one will how to solve it out. Let's come to that point. So here is 1, 2, and 3. So for let's say this one is A, this one is say B, and if I imagine this one as C, then B A is given. That is 10.5909. Rotational constant is given. Then B is not given, and BC is not given. Okay, since you already know that B is equal to 8 divided by 8 pi square I C. So now value of I will be changed, and rest of the value will be remaining same for all the three equations, either A, B, or C. That these three terms will be remain same. Hence, if I find out B, this one, okay, if I simplify it. So as I already shown you that how to calculate out the value of I. If it is given, the B is given, H already Planck constant 66 already known. So 8 pi square. So pi value already we have known. C value already we have known. So how we can find out the value of I? So if the value of I can be calculated out, so the rest will be easy. So how can we go through them? Go through the proper way. Say mu R naught square. So here it is mu R naught square. So since total body length, even after they will have different isotopes, their bone length will be remain same. So this one will be remain same. So B and C will be different out. So reduced mass can be calculated. So BA by BB, and hence you can calculate out the rest of the values. Okay. So hope you just solve it out whether how to figure it out how to calculate out the values of B for H30, 17 or the second one. So if you can solve out, then just screenshot it out to me, and either in WhatsApp or in the comment. Or if you have any difficulties in solving out, or you need the proper solutions, then I will provide you in the descriptions. Go through that link in Google Drive. I'm just providing you the solution. So these are the way to solve out. So better you just go through, and these are all the questions being collected from the manual book. This is Physical Chemistry, Molecular Spectra, Fundamentals of Molecular Spectroscopy by Manual. So just go through it, and hope you just calculate out all the values. Similarly, this one is another simple questions, which has been rotational spectra is given. Lies at demand, that means twice B, value of twice B is given. So from B, value of B, I can calculate out the moment of inertia as well as the bond length also, since I have already molecular mass of hydrogen can be calculated out, or molecular mass is already known. H1 is 1 and F1 is 19.